So now that we're familiar with the standard normal distribution, let's go ahead and see how to apply it to some quote-unquote real-world examples. So remember, we can map any normally distributed continuous random variable measured onto the standard normal curve using the formula z equals x minus mu divided by sigma. X is your individual raw score, mu is the mean of the distribution, sigma the standard deviation of the distribution. We'll do it once using a table. To use the table is only for the standard normal distribution, right? In the standard normal distribution, mu is 0 and sigma is 1. So to do that, right, in order to use a table, we need to convert our raw score into a z-score, and we'll use the formula above. When we do it, then we'll have to draw a line at your score from step 1 at your z-score, determine which area you need to find, right? So are we on the left or the right? And then we'll look up that area in the table. Okay? And then I'll show you how to do it on the calculator, which of course is going to be much easier. Okay, so here we go. So let's do our first one. So using the table. So contrary to popular belief, the average body temperature is 98.3 degrees. With a standard deviation of 0.73. And here's where I stole that little piece of data. So if a person is chosen at random, what is the probability that the person's temperature is less than 97 degrees? So we're going to, let us go ahead and mark our axes down here with both the z-score and with the raw score. So let's do the raw scores first, like the actual temperatures, because, right, that's what we have already. So average is 98.3, so that would go right in the middle. Okay, so we know the z-score for that would be 0, right? So here are my z's and here are my x's. So the standard deviation is 0.73. So if I go out one standard deviation on either side, right, if I go to the positive side, I'd add 0.73, and to the left, I'd subtract 0.73, and I could get those raw scores. So those are a little bit trickier to find, and I don't have a whole lot of room. So I'll just go ahead and mark my z-scores down below. And now let's go ahead. So we're going to use our table, so I'm going to convert that into the temperature that we're interested in. So 97. I'm going to convert that into a z-score. So actually, before I do that, let's do one more thing. What is the probability temperature less than 97? I want to translate that to math. So that's probability that the temperature, right, which is an x, so x is standing for our temperature, less than, so draw a less than symbol, 97. So once I do that conversion, once I do that translation, I'm seeing that I'm going to be looking for an area to the left because that's how it's set up. So I need to convert now. Let's convert 97 into a z-score. So x equals 97 corresponds to a z of what value? Okay, so our formula, so z equals the raw score minus the mean, right? The mean, 98.3. Divided by the standard deviation, 0.73. So I'm going to go ahead and do my calculator, which is probably going to be a little, oh, we can kind of see it there. Okay, so I want to do parentheses around the top. So 97 minus 98.3 divided by 0.73, so negative 1.78. So that value, so I'm on my z's, right, negative 1.78. This would be where 97 is up on the x-axis. And I want the probability that I get a value less than that, so I will be to the left. So that z was negative 1.78. I've shaded the region I'm interested in. It's very handy. And now I'm going to grab a table. So this is a table that's different than the one I did before, so now I'm going to look at this key. So this key gives me the area to the left of a particular z value, which is exactly what I am interested in. Okay, so let's see. Oh, but this one only has, I only have the positive side. Yep. Okay, so let's think about how I'm going to have to fix that. So let's just look up positive 1.7 and then find the 8 across the top and find whether those two things match. So that's 0.9625. So I'm just going to do a little work over here on the side. So 0.9625. And I'm going to draw a picture. So this is a little cheat sheet picture. And that is the area to the left of positive 1.78. Okay, so now I'm going to move my table. So I want the area, right, left of negative 1.78. So that's going to be the same as the area to the right of positive 1.78. So how am I going to find the area to the right if I'm given the area to the left? So remember, the total area is 1, right? So to get the area that's not included in the 0.965 or 9625, I'm going to do 1 minus 0.9625. So again, with my calculator though. So 1 minus 0.9625. So the area either here to the right of positive 0.178, or if the one we're interested in, to the left of negative 1.78 is 0.0375. So thinking of that in probability, probably we would say a percent. So the probability that a temperature is less than 97 degrees is 3.75%. So if we wanted to do that same example using our calculators, our calculator does not require us to come up to translate to z-scores, because it's more than happy to do that for us. So again, I'm looking for the area, the function on our calculators that does that. It's listed in the distribution menu, and it is the normal CDF. That's the one that tells us area. So this time I want to give it its lower value, so I'm going to the left, right? So I need the furthest left value. It's set up right now at negative infinity. It defaulted. If yours didn't, you can put that in, or you can just put in some other large negative number. And then I want to put where I'm stopping. Now I'm going to do the actual temperature, so I'm going to put in 97, because what I can do with my calculator then is tell it using what mean. Right? Converting to a z-score is a simple arithmetic operation, which your calculator will do for you. So the reason why we have to do it if we use the table is because the table is only set up for the standard curve. Right? Calculator will do the conversion for us. So for the mu, I'm going to put the 98.3, and for the sigma, I'm going to put the 0.73, and then I'm going to paste. Again, if your calculator didn't prompt you like mine did, that's the order: smallest, so for this left, comma, for this right, comma, mean, comma, standard deviation, and then enter, and there is that same value, 0.0375. So remember, it was distribution, normal CDF, and then mean is 98.3, and sigma 0.73. And that tells us again the area, which is the same as the probability of 0.0375. Okay, so let's do some more. Sometimes, if we want the raw score that corresponds to a particular percentage. So using our temperature example, and I'll copy that over here so we know that the mean is 98.3 and sigma is 0.73. What temperatures will constitute the middle 90% of all normal body temperatures? So we're going to do it on our calculators. So I'm going to draw the picture, and I want the middle 90%. And we have, so that means, right, we have 10% to share. So each tail is going to get 5%. So the reason why I need to know that is because the function on our calculator, right, inverse normal requires area to the left. Okay. So let's just see what the inverse normal is going to do for us. Distribution, inverse normal. So it wants the area. So let's find this left-hand side first. Okay. So if I want, first I tell it the area to the left. So it's 5%. So I would type in 0.05. And then I tell it the mean. So I'm going to just give it my temperatures. I don't have to do the conversion if I'm using my calculator. Sigma 0.73, paste, paste. So that temperature on the left side would be 97.1. I'm going to go ahead and round that. So then, if I wanted to find the value, the temperature on the right-hand side, so that would be, again, the thing that's going to change is that area value. So now the area to the left, right, of our right-hand temperature is going to be the 90% in the middle plus the 5% right further on to the left. So 90 plus the 5% would be the area I'm going to look up. So I'm just going to change that 0.05 to 0.95. And that gives me 99.5 degrees. I'll put my degree symbol on so we know those are temperatures. Right? Those are the temperatures that correspond to, right, those upper boundaries, or the middle 90%. So 97.1% or 97.1 degrees and 99.5 degrees. 90% of people will have a body temperature between those two values. Now, if your calculator does not do that, then you would find the 0.05 area, find that z-score. I'm going to use this table real quick. So 0.05 looks like that's our area. So that corresponds to, oh no, this is the other table. So I need to do 1 minus the points. So 0.45, sorry, 0.45, here we go. So 1.64 or 1.65 for your z-score. So you could use a z-score of 1.65 here, just to show you how it works. X is what we're solving for. Mean is 98.3. Sigma is 0.73. And we're going to solve for X. So we do that by multiplying both sides by 0.73 to start with. So that cancels my denominator. So 0.73 times 1.65, so 1.2, and then I'm going to add, right, the 98.3 across to get the x by itself. There's that 99.5, right, that we found from our calculator. It's kind of on the other side of my calculator here. To find the other one, you do the same thing, except you'd use a negative 1.65 there. Okay. Now it's just a little bit of a discussion about percentiles. So remember, area equals probability, right? And the probability is a percent. So we can find the percentile rank for different raw scores using our standard normal distribution. So again, let's stick with our temperatures. So mean is 98.3, sigma is 0.73. So a person with a body temperature of 98.0 degrees would be in what percentile? So percentile, right, tells you the percent of the population below that value. You'd think that my curves would get better, but they really don't. So mu goes in the middle, so 98.3. So 98.0 is less than that, so I'll draw that line to the left. And I want what, so the percentile tells, right, gives the value of the area to the left of the score, right, so 98. what percent is to the left of 98. So I'm looking for area. Area on my calculator is that normal CDF. Normal CDF, lower, so I'm going to the left, so my lower is negative infinity. I'm going to stop at 98. Plug in your mean, 98.3. Plug in your sigma. So they would be in the 34th percentile. So that area is 0.34. So that means a person whose body temperature is 98 degrees is in the 34th percentile. 38% of the population is less than, has a body temperature less than a temperature of 98. Okay, so what temperature would correspond to the 95th percentile? So this time I know the percent, right? And I want, so the lower 95%, 95th percentile. What temperature, what x value, right, cuts off the lower 95%? So that's inverse normal. This time I know the percent, I want the value, so that's inverse normal. Inverse normal, again, the idea is you do the area to the left, tell it the mu you have and the sigma you have, and 99.5. Oh, we found that one already, didn't we? So 99.5 degrees, right, is the temperature that corresponds to the 95th percentile. 95% of the population has a resting body temperature less than 99.5 degrees. Okay, last thing here before we practice, I think I've got some practice, is Central Limit Theorem. So the Central Limit Theorem lets us answer questions about the probability that a group of people will have a certain average. Okay. We would expect the probability, right, for a group to be different than the probability for an individual. So it'll answer the question, so what is the probability that the average body temperature of a group of 15 patients is less than 98 degrees? So the formula for converting it to a z-score is super similar, but here's where it's different. So it's the mean of our sample, so x bar is the mean of our sample, the one that we're interested in, that we're asking about. Mu is still the mean of the population. Sigma is the standard deviation of the population. And then that n, that is the number in your sample. So what we're doing is we're making that standard deviation smaller because we're dividing it, right, by a number that's going to be bigger than 1, because the number in your sample can't be less than 1. So let's see how this is working. So if the original variable is normally distributed, then the distribution of sample means is also normally distributed. And again, the standard deviation of the sample means is smaller than the standard deviation of the individuals. Now, we have a little workaround. If the original variable is not normally distributed, if it has a skewed distribution, then the distribution of sample means is only considered normally distributed if the sample sizes is greater than 30. So if we were looking at some sort of variable that was skewed and we wanted to see, like talk about the probability of an average of a group, that group size would have to be 30 or larger in order for us to do this. Okay, so here we go. The average teacher salary in North Dakota is $37,764. Assume a normal distribution with sigma equal to $5,100. So what is the probability that for a sample of 75 teachers, the sample mean, so sample mean, that's X bar, is greater than 38,000. And we're talking about probability. What's the probability that X bar is greater than 38,000? And we know, so the average is 37,764 and sigma 5,100. So I'm looking for a probability. So let me show you how we can do that on our calculator. So I'm going to use, again, I'm looking for the probability. Probability is area, and that's normal CDF. So distribution, normal CDF. Let's draw the curve. So the average in the middle, that's that 37,764. The one we're looking at is what's the probability that our average is greater than 38,000. So that'll be to the right of the mean. And we want to be greater than that. So I'll shade the right-hand side. So that vertical line corresponds to our 38,000. So my lower limit is going to be the 38,000. My upper limit, so it goes off forever to the infinity side, right? So I could either do infinity, or I'm just going to put in a really, really big number, like 100,000 mu. So that's the, right, it's the same symbol. It's the population average. Now here's where it's going to be different. So for my standard deviation, it's the 5,100. But since I'm talking about the average for this group, I'm going to divide that by the square root of 75, and I can just have that there in my sigma line. So that probability, right, that a group of teachers has an average greater than 38,000 with this situation, right, is 34.4%. Versus, what's the probability an individual teacher's salary? So that would just be an X, not an X bar, is greater than 38,000. All right, so the picture looks the same. The mean of the population is still the same. But now your 38,000, right? Again, it's to the right. So the thing that's going to change is that sigma. So instead of dividing by the square root of 75, I'm just going to use my delete key and get rid of that. So that, right, it's more likely that you could find an individual, 48.15%, an individual with a salary greater than 38,000, then you, right, it's more likely 48% chance versus a 34% chance that a group of 75 would have that kind of an average. Right, and the reason is that, right, if you have a group of 75, some are going to be high, some are going to be low, they'll sort of balance each other out. So, average time it takes to pack a box of apples is 130 minutes. So mu is 130. Use 5 minutes for the standard deviation. What's the probability that a person, so that's just a single, so probability X longer than, so greater than 138. So do you want to try to do that on your calculators before me? If you want to get a head start, go ahead and pause. Otherwise, here we go. So I'm looking for area. So normal CDF, my lower value. Let's do my picture. I keep forgetting to do my picture. So 130 is the middle. I'm looking for 138, so that'll be on the right. And I want to be greater than, so I'm going to shade to the right. So this value right here, that's that 138. So I'm going to use that for my lower value, 138. My upper value, it goes on forever. I'll go ahead and leave the 100,000 since it's there. The mu for this situation is 130. The sigma is 5. And we'll paste it onto my home screen. So it looks like there is a 5.5% chance that an individual, right, given this setup, that it would take an individual more than 138 minutes to pack a box of apples. Versus, what is the probability that a shift of 10 workers averages more than 130 minutes to pack a box of apples? Right? So N is 10. And this time, I'm actually going to look at 130. So 130 is my mean, but I want to know what's the probability that that group takes more than 130 minutes. What's the probability the average for our group is bigger than 130? Oh, change that lower limit to 130, thank you. And instead of 5 for my sigma, I have to divide it by that square root of 10 because I'm looking at for my group. Oh my gosh, look at that. So since it was still the average, so this is our calculator's version of saying 0.5. 0.499999 is our calculator's version of 50%. Okay, here we go. Average height of a stat student at Wenatchee Valley College is 66 inches with a standard deviation of 4.2 inches. What is the probability a student, single, so just X, is taller than, I keep doing a lot of greater thans on this one, greater than 68. So normal CDF, lower limit. So 66 is the average, so that goes in the middle. 68 is bigger than that, so I'll put it on the right-hand side. And I'm looking at greater than again. So my lower limit is 68. My upper limit, I'll keep it there. Mu this time is the 66. And standard deviation, 4.2. So 66 for my mu, 4.2. I don't divide it by a square root of anything because I'm just talking about the individual. So 0.317, or right, 31.7%. There's a 31.7% chance I'll get a person taller than 68. Okay, so this next one, what is the percentile rank for a person who is 68 inches? So the percentile, right, so here's our 66 in the middle. Here's the 68. So percentile rank, that means the area to the left of that value. So since we just found the area to the right of this 68 height, I know that I can find the area to the left by doing 1 minus, right? So the percentile rank is the same as the percent, the amount of the area that's there. So if I do 1 minus 0.317, that tells me the percentile rank of that height. So a person who would be 68 inches tall would be in the 68th percentile. Okay, one more example. So the average on a standardized exam is 72. So I'll go ahead and do these as I go. With a standard deviation of 5.6. What is the percentile rank if a person scores 80? So there's 72 in the middle, so 80 is bigger than that. So here's my 80. Percentile rank, I need to know the area left of 80. So I'm looking for area, so it's still sticking with that normal CDF. So my lower limit. So now 68 is not quite low enough, so maybe I'll just put 0. My upper limit, 80, that's where I stopped shading. The mu for this one is 72, and the sigma was 5.6, and we'll paste. So a person who scored an 80 has a percentile rank of 92.3, or we'd say maybe the 92nd percentile. Now, if a class of 30 students took this exam, what is the probability that their class average is less than 70? So I used X bar for the class average, right, because it's from our sample, and I know that N is 30. So let's get that picture. Again, 72 is the average for the population, so 70 would be less than that. So what's the probability that our group has an average less than, 70? So again, I'm looking for area. That's that normal CDF. The lower limit, 0 is good. Upper limit, that's where we stopped shading. So that's going to be 70. The average is 72 still. Oh, sigma. So this, because I'm talking about the average for our group, right? So now I have to change my sigma and divide it by the square root of how many? And the N we had was 30. So there is a 2.5% chance, or I should say 2.5% of all classes of 30 who take that exam are going to score, or going to have an average less than 70.